So the rank of the matrix indicates the number of linearly dependent dimensions present in a matrix. I will just explain you on a brief note. Consider a matrix A with dimension A1, A2 and A3. The dimensions A1 and A3 are said to be linearly dependent because they can lie on a single straight line. In other ways, the dimension A3 can be obtained by using the dimension A1 just by scaling it up. Say this is the matrix, this is the dimension of say 1, 2 and 3. Then the dimension A3 can be easily obtained by multiplying certain multiplication factor, right? So these two matrices are linearly dependent on that. Considering that if we multiply a linear term, we are going to get one of the other dimension. In other way, we can held up or we can hold only any one of these dimension and drop off one, so that we'll be arriving at a lesser dimension matrix. So that was the major intention of the whole theory which we are talking about, right? So that's why we are deciding the rank of the matrix. So these there are other dimensions, say the A1 and A2. These two are non-linearly dependent, right? They do not depend linearly on each other because they are oriented in a different directions. So we cannot consider or ignore the A2 or A1. So we have to consider these two dimensions in order to obtain the final matrix. So according to the definition, the rank of a matrix indicates the number of linearly dependent dimensions present in a matrix. So for our discussion in the matrix which I have considered, our rank of the matrix A can be 2. So this is about the rank term. So coming back to a final equation which we discussed. So this U M cross R indicates the singular matrix containing the eigenvalues of rth dimension. In other way, suppose if we decompose this matrix and we will get the eigenvalues or eigenvectors, and if we form this into a matrix, then it will be singular matrix with a column only, not the rows, with the highest rth dimension. Then there is another, and how can we obtain this? We can obtain this by multiplying this matrix A with A transpose. That is A dot A transpose. So we are obtained with the U matrix. Then there is another matrix called V transpose, that is of dimension n cross R. So by obtaining this U matrix, we will be basically mapping term to term, right? So from term to context, we are already converting it internally into term to term matrix. Then other one, that V transpose, will be a matrix with eigenvalues with a rth dimension, but here we are taking the context to context relationship. So this will be also a singular matrix with a column. This will be also a singular matrix with columns, but here the term to term matrix will be present. Here the context to context matrix will be present. So and the final one which will be left with will be the diagonal matrix, that is sigma with dimension r cross r. This will be the diagonal matrix. So I will better explain this with a diagram like this. So I have splitted this into U M cross R, sigma r cross r, and V transpose r cross n. As I mentioned, we can get this U M cross R by multiplying A into A transpose. Then we will be getting this individual column matrix or the individual singular matrix, and I will arrange those into another new matrix. Then this V transpose, or it is also obtained by taking A transpose into A. The only difference between these two would be, here we are obtaining it by multiplying A into A transpose, but here we are getting it by multiplying A transpose into A. And other difference would be, it will be a term-term relation, this will be a context-to-context relation. And the final one, that is diagonal matrix, as I shown in here. So this will be getting the rth dimension and we are arranging the elements in the diagonal. Fine. So we are arranging the matrix into a diagonal matrix, and the highest one, the highest R value would be at top and lowest R value would be at the bottom. By this way, we are reducing this dimension of the m cross n into a smallest size or a smaller dimension by multiplying or by decomposing the matrices into 3 different eigenvalues or eigenvectors and multiplying back them to the original form.